Welcome everyone to the third session of the first day of this conference. The chair for this session will be Professor Purushottam Rath from CMI. Over to you, sir.
Thank you, Jyotsna. So I welcome everybody for the final session of the first day of this conference. It's my pleasure to introduce Professor Bernhard Heim from Aachen University, and he will be speaking on from Ramanujan to Rota, Lehmers Conjecture. Professor Heim.
Thank you very much. Thank you very much to the organizers. I think you've done a great job, especially in this short time. I mean, normally it's like 1 year planning and you just done it very quickly, at least in a very short time. And I also would thank to Ramki for his really touching friendship since many years. And maybe I will talk a little bit more on Sunday evening. Okay, and when there would be no COVID at the moment, maybe I would be in India, but it turned out to be differently. Yeah, today I would like to talk about the Lehmers Conjecture, which is very, of course, close to the Ramanujan tau function. And I would like to motivate the philosophy of Giancarlo Rota, Italian guy at MIT on combinatorics, who I also will show you quote, and hopefully my talk will convince you that it's worth to go in this direction. So the plan is to give an introduction, to talk a little bit about background and around the Lehmers conjecture, then introduce and talk about certain polynomials which had been found in 1913. I think they appeared the first time in that way by Italian, or the Italians seem to be very prominent in this talk, Francesco Darche polynomials. And then I will go in two directions, which I call the exponential case, and there will be a geometric case, and then there will be a general approach. And if there's time, about reason research in using this approach in directions of inequalities, log concavity and the Bessel-Ono type inequality. So the basic object, or the starting point today, is we are looking at the infinite product 1 minus x to the power of n, or in the modular language 1 minus q to the n to an integer power r. And we are looking, which we have seen today already in the first talk, about on the coefficients. When r is an odd integer, we will have up to some factor modular forms of half integral rate. And I also refer to that talk when we talk about non-vanishing and vanishing of coefficients. So it's well known, of course, when r is equal to 1, then we have this famous formula involving the pentagonal numbers on the right side. When r is equal to 3, Jacobi, the triangle numbers. When r is equal to -1, that means when we have 1 minus x to the power of n in the denominator, we have the coefficients will turn out to be the famous partition numbers. And when r is equal to 24, we will get the Ramanujan tau functions with a shift, because I start by 0. And the Lehmers conjecture, which predicts that all coefficients are non-zero, in this language would say that the n-1 coefficient, when we plug in 24, is non-zero. So that's the main theme of the talk. So Giancarlo Rota said he wants to be remembered that all sorts of problems in combinatorics should be can be viewed as a problem about location of zeros of certain polynomials. When we go back in some sense, you already can see that A and R can be considered somehow, at least as a function of R. And when it turns out it can be considered as a polynomial, and then of course the zeros seem to be quite reachable. So what does it mean? And it means there will be certain polynomials, I mean the coefficients, more general even as in a parameter x. On the right top side, you see a plot of the polynomial of degree 500. That means and the blue color are the real roots, and the red color are the complex roots. And as you may remember, also related to Borchardt products, when you have the Dedekind eta function, it can be written as exponential, and in the exponent you get the sigma, the divisor sum function, and when you take the logarithm and derivative, you will get a recursion formula. And the polynomial or the polynomial would look like, or the recursion would look like this here. And when you plug in, for example, x is equal to 1, you get you would not see the x here. Normally the n is put on this side. This would be the recursion formula then of the partition numbers. Maybe you have seen that. But you see here, this can be generalized completely, not just at a point 1. It can also include the tau function and all the others which are mentioned in the example. And so the question about lemma is minus 24 a root or not a root of these families of polynomials? And it will turn out, as you see here in the recursion formula, that these are really polynomials. And the point is that that's the hope. When we have polynomials, we have only n, when the degree is n, we have n roots. So when we can find n roots which are not equal to minus 24, we would be done. But it turns out, as you see here, when you look here already closely, minus 24 would be the most important value we're looking at. And you see here, it's like a cloud. So it also shows the complexity of the problem. Here, it's much simpler. But here, minus 24 is, and also the other points here are like in a cloud. So here, when we zoom in, I show you also the polynomial of degree 1000, and you see it looks similar. Here we have a cloud or a lot of also complex roots. So here we have the red ones, that means only real roots. But you already see here there's some pattern. And the question is, of course, is it possible to understand this pattern from a global viewpoint? Now this is, for example, this is 1000, the degree 1000. And this is degree, this is degree 500. So in some sense, they look similar. We have always here the red dots, and here this kind of staccato blue dots. Okay, now I have, okay. What I also done here, and it was also on the cover sheet. This is joint project since now 3-4 years with Markus Neuhauser, who was also with me in Oman. When we zoom in the case of degree 500, and we look at minus 24, which is the important point, because we done I will show you also in the next slides that it's important, or it's technically useful. Instead of to the power of r, we take to the power of minus r, because then we get then all the coefficients of the polynomials will have the same sign. And here you see the minus 24 is surrounded by complex numbers, and so minus 24 is not a root, especially, but this is not the general picture. There could be also, this could be the first guess, but there could be also for some other degrees, blue dots around. Now, by looking at these R powers of the Dedekind eta function, the first thing which come into mind is, okay, let's study these integer powers. And it turns out, as I already said, when you have to, it's good to distinguish between odd power and even power. When you have odd powers, you will end up with modular forms of half integral weight, because eta has the weight 1/2. And in the even case, you have classical modular forms. Now, it's also known when you asked about high rate of vanishing, or in other words, when it should look like a theta function, then this is only the case if and only if r is equal to 1 and 3. That means when you take eta and eta to the power of 3, a lot of coefficients are vanishing. When you take even powers, it's by Serre, and using results of Ribbet, you have a lacunary coefficient rate. That means also a lot, but not so many. If and only if you have the powers 2, 4, 6, 8, 10, 14, 26. So the power 12 would be the first case. It means weight 6 modular form, which is not lacunary. Now, what is known? Already in 85, when Serre proved his result on the lacunary in the even case, he gave a table for the odd case. In the odd case, when you have the power r is equal to 5, he gave this table and left the interpretation to the reader. Now we have seen in the first talk today by Dipendra that when you have modular forms of half integral rate, especially Hecker eigenforms, and you have the coefficient a(n)l square, and n is square free and co-prime from L, then and different from 2 and 3 in this case, then when an is 0, then also a(n)l square is 0. And I call it sources. That means when you have the an, that means 1, 5, 6, 0, and so on. These are all square free numbers. Then you get also infinitely many coefficients which are 0. And the same is, and then there was in the table r is equal to 7 and 15 and nothing else. So that means for each number here, you get infinitely many coefficients which are 0. And in the case r is equal to 5, that means when you take eta to the power of 5, you have infinitely many sources. That means infinitely many square free numbers where you start. And we extended this and calculated, we wanted to know what else is happening. When you take eta to the power of r, then you would have exactly what Dipendra wrote down. But here we skipped the q to the 1 divided by 24 in the beginning to have some standard notation. Then you get this kind of sequence. And we checked that in the case eta to the power of 5, it looks like that there's infinitely many sources. That's an open question. That's also a question on the non-vanishing or the vanishing of this. When you look at the formula for Alsper-Schee, that when you have these a(n) square absolute value is equal to the twisted center of an L function, but it seems it's not so easy to apply this formula in the sense that you really show non-vanishing or vanishing. I mean, non-vanishing seems to be much easier. Now, but it turned out, which is, I think, quite interesting, exactly these numbers in the table of Serre, 5, 7, 15 appear. and he had said nothing to the others. And we calculated this to the power of 10 to the 10 here, and there's no new source appearing, and we done this even up to 549. So it's like the Lehmer conjecture. It looks like the Lehmer conjecture for odd powers. And in the even case, we also checked to a very high power. We even went to the 10 to the power of 11, and we found out until now that only these Serre numbers, where we have lacunary, lead to vanishing of coefficients, and for all other powers, there's no single case known where we have vanishing. That means the Lehmer conjecture, which first was motivated and spelled out for the Ramanujan tau function, seems to be true or could be conjectured for all other powers. Now you could say, okay, to the power of 48, for example, which is weight 24 modular form, this is not a Hecke eigenform, so maybe it's not true. But it turns out there's this Maida conjecture on the Galois group of the characteristic polynomial of the Hecke operator, and we look at that in the weight 24 case. It's equivalent to the conjecture that no coefficient is vanishing, that of the delta to the power of 2 function. So there's some evidence that this is maybe true in general. Okay, so as already indicated, instead of just putting to the power of r, let's put it to a complex number and look at this definition. And it turns out, and you have seen, I already indicated that in the recursion formula, that these coefficients are now polynomials in this variable, and they are actually of degree n. So what does this mean? This means, so first of all, from the recursion, you can see when we multiply by n factorial and divide by x, then you get the normalized polynomial of degree n minus 1, and all coefficients are positive. They are even not 0. As an example, and they can recursively, of course, written down. When you take, for example, the third polynomial, this has now 2 zeros. It has 0 x minus 1 and x minus 8. For example, it means when you put eta to the power of minus 8, then the third coefficient is vanishing. So there's some kind of duality in the argument. So now so the powers are the arguments of these polynomials. Now with this normalization to the minus set, it turns out that all coefficients are positive. That means the non-trivial real roots, I mean, 0 is always a root. The non-trivial real roots are all negative. And we observed, which is quite interesting, either you have integer roots, which we know by Serre, but then the rest is a polynomial of Q. That means the degree of these algebraic numbers, which are roots of these polynomials, are increasing. I think this is this observation which is interesting in itself. Now, when we plot it, when we take now all polynomials from 1 to 100 and plot, so you have here the polynomial, and we plot all the roots. The blue ones are again the real ones, and the red ones are the complex ones. And here we plotted the real part of the complex one. You see, not just when we have here 1000, we always have a certain pattern that here we have also complex roots, and here it looks very like, it looks almost like interlacing property. For example, when you go to the first 10 polynomials, here you have the roots. In the case n is equal to 10, it's the first case when a complex root appears. again, when there's no dot, which no blue dot at -24, that's actually what Lehmer is saying. What is an open question? And we proved in some cases that, for example, when n is a prime number, then all the roots are simple. This is proven, but not in general. And it looks like we proved that, we checked that up to 2000, that all the roots are on this left half side of the complex plane, which is the so-called Hurwitz property. That means when you have a polynomial, that all the roots have negative real part. Now, is it possible to show that no roots, that certain numbers are never appear root? And actually, so we asked quite simple question: is it possible that I, the complex number I on the imaginary axis, is a 0? And it turns out no. Actually, more general, with Florian Luca, we proved that when you have a root of unity, and you know that this root of unity, nth root of unity, is a 0 of the nth polynomial, then it has to be equal to -1. Now, it turned out that these kind of recursion formulas are of, when you look at it closely, they are of hereditary type. That means they have not a finite length. I mean, the length is finite, but in the recursion, the n appears here. Normally, you have a k here. That means you have a k order difference equation. So the question is, how can you study such equation? And we said, okay, let's approximate. Here you have to think about sigma of k. That means the sum of the divisors of k. So maybe it's a good idea to generalize this function and to find upper and lower bound. For example, sigma k, you have the lower bound by k, and the upper bound, you have a nice one by k square. So we said, okay, let's study this differential equation. Again, you get polynomials. And you get back, when g is equal to this function, you get back our original polynomials and values. And when you put in the identity, it turns out, which is quite, I think, interesting, and that you get actually the Laguerre polynomial, the associated Laguerre polynomial here of degree n-1, which are orthogonal polynomials. And then, of course, you know, the roots are interlacing, are real and interlacing. So from below, you have some nice polynomials. Our first result in this direction is we proved when the argument is larger than a constant times n-1, then these polynomials have this growth condition, which when you do this by induction, you see when the set is larger than k times n-1, especially when it's linear, then all the values, and now indirectly all the coefficients are non-zero. But you see this bound goes with n. So that means after, it does not solve our problem with -24. This is meanwhile published in Hamburger Annalen of Hamburger Abhandlungen in the beginning of this year. And I also would like to mention there was a result of Constant using representation theory of affine Lie algebras and affine Weil groups, and results of Hahn in the connection of Nekrasov or Konkov polynomials, which had actually the bound root of n-1. So this was a quite big step And it turned out when you calculate the root bound, it's quite close to what you see numerically. Now the next step, which turned out to be quite, how to say, rich in going even deeper in this topic, is when you also generalize, there was an x divided by n, when we also say, okay, let's allow here hn. So hn could be 1, could be n square, could be even something between. That means we could approximate our original problem by varying the g here and the h here. So now it turned out that with the same constant, that means the result on the non-vanishing, we could prove. So we have a proof for general h non-vanishing, and it has to be increasing in this case, but it can be also generalized, and a general g here. And also we get this non-vanishing. But now the interesting thing is somehow this qn, which we call it, so we call it now p, just to make the notation simpler. So p is denoted when we have x divided by n, and q when we have x divided by 1. And it turned out like that the q case, we could prove certain results similar for the q case and the p case, but the good thing is, or the interesting thing is now the q case is somehow the compact case, because here you see there's no n involved. So for all these sets which are larger than this kappa, we have a non-vanishing. Now, what kind of functions, polynomials could be behind this? Let's do so we done the case when g is the identity for x divided by n, so we get Laguerre. It's quite interesting when we now take x and take here identity, we get actually the Chebyshev polynomial of the second kind. So in these two cases, we get actually orthogonal polynomials. So it means also that our original recursion formula could be reduced to a 3-term recursion formula. And now you can also imagine maybe there's a pattern here. Now the plot in the case of the Q polynomial looks like this. So somehow similar pattern. Also the complex are here. It looks quite interesting. And maybe there's a structure behind why these somehow ellipses, circles appear. It looks like an arrow here. But again, and here as we have this kappa, and the kappa is a little bit larger than -10. You see here we are quite close what to expect. Now this is just to see, here is the case of p, that means x divided by n, and here we have the q, that's the x divided by 1. And somehow here you see this goes to infinity, but here still, but the q polynomial seems to be quite easier to handle. Here again, the plot with the roots 1, 0, so all the polynomials up to 100. Here the p version, here the q version, and here they are, it's, as I said, indicated it's like the compact case. But here's also like some internal barrier which we could not figure out how to prove it. Here's just an overview on the percentage of complex roots and real roots. So it's like 2/3 real roots and 1/3 complex roots, and similar for the p version and for the q version. And again, the idea is it seems to prove something for the q polynomial first, and then transfer it to the p polynomial. For example, maybe you know there's an old result of Laguerre saying when you have a polynomial with real coefficients and real roots, and you divide all the coefficients by, so the k's coefficient by k factorial, then this new polynomial has also real roots. And actually somehow, and we also have put it on archive, that's actually how you transfer the Q polynomial to the P polynomials by having this factorial K factorial in the K's coefficient. So once we have proven that these are that the Q polynomials have only real roots, it's also possible that certain P polynomials have also real roots. So there is some kind of transformation possible. So to summarize this, this is the recursion formula for the P polynomial. This is for the Q. And it's possible to write down formulas for the coefficients and also transformation formula from the coefficients. They have the same kappa for the Crows condition and the non-vanishing, at least numerically. I mean, it does not say that when we have the true barrier, that's the same kappa. And actually, it's not quite true, but they are very close. Then this Horwitz property we claim as a conjecture should be true. And I just want to mention when we have this recursion formula, you know, it's not a fixed order in general. This is the same in the Q version. This somehow cannot really be handled. I mean, when you have, as you may know, when you have recursion formulas or differential equations where the coefficients depend on n, you only get asymptotic results by, you know, there's this famous theorem of Poincaré, and then improvement by Perron. But this is for a fixed k here. So the question is it possible to have a generalized Perron-Poincaré asymptotic formula for solutions? Open question. Now in the Q version, the coefficients are not depending on n, and there's an approach actually of a discrete Volterra type differential equation where this actually can be handled. And when you do that, you get actually something like this here. The set transform looks like this. That means when you put all the GNs, the coefficients, as a new function here, then these Q and these Q coefficients here can be expressed by which we call some geometric type of series. And now we are in business, because now you can ask about poles, and then you can use all theorems, function theory, when you have a pole on the border, that the quotient of this Q or the set expansion of this in the limit go to the pole, and then you even can get asymptotics. And actually we've done this for the reciprocal of the J function, of the Klein J function. It turned out actually we could prove that these coefficients, especially for this value, are non-vanishing and actually change signs like a polynomial, which you expect, which has no zeros outside a certain zone and goes to minus infinity. So up to the degree the sign is changing. And this was reproving a result of Asai, Kaneko, and I only Nimai, I think, about 20 years ago. Actually proved it also for the Weber function, which is the cubic root of this. So the method has much potential. We also done this for reciprocal of Eisenstein series, and we reproved some formulas, asymptotic formulas of Ramanujan, and later of Bernd, and then Brinkmann and Kane. And so this was quite surprising, that the original problem on the polynomials and generalizing the x to the divided by n reaches to such kind of results. So you get actually this, which I indicated in the beginning. These p polynomials can be sought, or can we have this generating function. Here h is equal to n, and when h is equal to 1, you can get this generating function. And as I indicated, these polynomials or the values have some similar properties. So there's hope to get from this, I would say, more easier accessible approach properties of our original problem. Now to end my talk, going back to the Ramanujan tau function, in this famous table in this paper in 1916, you can also find it in the book of Murty on the legacy of Ramanujan. The first, you have here the first 30 coefficients, and it's well known. This led to Hecke theory, Galois representation, the linear. But what was not mentioned until now, or at least not directly, how can you interpret the sign change of these coefficients? And there's much activity in general on the sign change of these coefficients, and several people in the audience worked on that and still produced and published very nice results. What you can do in this concrete page is the following. When you have sign change, which starts, this means the polynomial somehow behaves like it should behave when you have a polynomial of degree n. Now we have to shift by 1. And so the first case, when you go here from 6 to 7, means in our interpretation, and we can show it, that a root appears and just changes the sign. That means the parity change gives you plus minus, and then a change just keeps it. And now you can also study, of course, the sign changes and the non-sign changes by looking at the roots of the polynomials I mentioned. Just to make a little bit advertisement, this was published also. This is the book which has been published by Ramakrishnan, Modular Forms and Related Topics. This was the birthday proceedings to also our friend Manikan, and so there this article is published. And just to end up my talk, these polynomials, surprisingly, can be described by the so-called Nekrasov-Okounkov hook length formula. So you see on the right side, again, you have this polynomial shifted, and here you have a generating, you sum over all partitions, you take the lengths, then you take the product over all hook lengths of a fixed partition. So you make the Young diagram, and then you count the arms and the legs, and you look at this product. So showing some non-vanishing here, which I talked about, think about our kappa, gives you also non-vanishing on this side. So now the big challenge is for example, from the combinatorial viewpoint, maybe one can use certain tricky things from the combinatorial viewpoint to prove something here, or vice versa. So there's work of Westbury, Hahn, Abate Hahn. He made 3 conjectures. We proved 1, we disproved 1, and 1 we gave numerical evidence. Case, Warner. Yeah, there's quite, and recently there's work of Hong and Zhang at MIT, who also gave evidence that what we conjectured actually that these polynomials here, that they are log concave, and they proved some partial result in this direction. So open questions. it's still open that these polynomials for sigma and maybe also others are log concave. It would be nice to have some theorems on the correspondence between these polynomials, which is very, very challenging to find Poincare-Perron type Volterra equation when the coefficients depend on n. Extend the result of Heim, Lucca, and Neuhäuser, which was proved by algebraic methods that certain numbers, algebraic numbers, cannot be roots of the polynomials. This seems to me quite, so I think this is maybe, but it's very difficult, but this maybe with algebraic number theory can exclude certain cases which maybe cannot be done by analytic results. From the analytic viewpoint, we try to prove some density theorems, prove that these are Horwitz polynomials. When we would have Horwitz polynomials, this would open the door to dynamics, because then the polynomials are stable, and then you can start with dynamic systems and study these kind of polynomials. And maybe -24 is not an attractor or something like that, and you can get some results. So I will skip the last part, which you can find on arXiv. When we look at positive powers, I mean positive in the sense of negative, that means you look at partition numbers, plane partitions, and so on, which is not our basic goal, but maybe when you have polynomials and you want to know something on the left side, maybe it's good to study the right side. Maybe there's a pattern here to study the right side, who knows? And so fine, and many people are involved in this. And this has also to do with log concavity. There have been conjectures, partly it has been proven by us. And because what we've done is we generalized combinatorial problems on inequalities of numbers, now in inequalities of polynomials. And the good thing is when you have a polynomial, a function, you can look at derivatives. And so this gives us a new method. And so there's this conjecture. You will also find on arXiv. It's now also published. And Brinkman, Kane, Roland, and Tripp, they proved some discrete conjecture and some kind of part of our continuous conjecture. And finally, there's also possible to study the roots. And when there's no root on the right side, it means the polynomial behaves as it should behave. When you have positive coefficients and you go to the right, it goes to infinity. That means when this is the last root, there's no root here. That means the inequality works here. So that's the way how to see from an analytic viewpoint. So I come to the end, and I would like to thank again. So that I skipped the challenges. And finally, I would thank again Ramki for his friendship. And this picture was made, it's already 2.5 years. No, we have 21, so it's 2.5 years ago when I and Professor Böcher, when we had invited, there was this beautiful conference, and then we moved. I don't know where we moved. We drove at night, and then it was wonderful. And then we also went to the birthplace of Ramanujan, and hopefully one of us can prove something in the direction I mentioned today. So thank you very much.
Thank you very much, Professor Heim. So anybody from the audience has any questions and comments? We have some time.
Bernhard, do these polynomials have a limiting behavior as n goes to infinity? Can one show some kind of log concavity as n goes to infinity or for the infinite limit?
Actually, that's actually you hit the core. I mean, in the Pn case, the problem is, of course, the coefficients depend on n. It gets larger and larger. It's not so clear. But in the Q case, actually, this is we try, for example, to prove that certain roots that every actually in certain cases, we actually try to prove that when you fix a real x in a certain area, in a certain segment, that it's a limit of zeros.
Mhm. Yeah, no, I was just thinking because Okunko has some proof of log concavity for this some kind of restrictions in the representation, but in the infinite kind of when you go to the infinite thing, there is. So I was just wondering whether there's some kind of.
Actually, I never thought precisely in the infinite and looking at log concavity. I did not look at that one. I will. I think it makes sense first to go in the Q case.
Okay.
But that's actually an interesting question because we are somehow located in some compact area somehow.
Okay. 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 Yeah.
Okay, if not, that's time to speak once again.